Hey guys, this is Cloudy, and we are back to solve this AMC 2008. Okay, let's see. Triangle ABC has AC equals 3, BC equals 4, and AB equals 5. Okay, so that's this right triangle over here. Let's just draw it. Okay, it should be a little bit longer than this. Yes. Okay, let's see. This is A, B, C. 3, 4, 5. Point D is on AB, and CD bisects the right angle. CD bisects the right angle. So, bisect. If it's bisect, then each of these is 45 degrees, right? They're all 45 degrees. This is D. Now, the inscribed circles of ABC and BCD have radii RA and RB respectively. ABC, okay, hold on. Here we have circles right here. Okay, of course. So when we're talking about inscribed circles, the first thing we'll come up with is yeah, we connect. We'll think of that at the area of like a triangle ABC is equal to the circumference of ABC. Wait, it's not circumference. It's the perimeter of ABC. It's not circumference. Circumference is for circle. P, sorry, P, the perimeter of ABC times the radius of the circle. The radius are A, and of course A B BC equals the perimeter of BDC times RB. Well, if you're wondering why that's the case, then allow me to show you. We divide this triangle into three triangles. Now, of course, the area of this whole triangle is equal to the area of the three small triangles added up, right? Oh wait, there's also, oh wait, 8, yeah. I kind of almost forgot, there's a half. So anyway, the area of this triangle is half times the perimeter times this side times the radius. This triangle is this half this side times the radius. This triangle is this side half times radius. Yeah, so it should be obvious. Yes, like these two is the case now. Okay, we're supposed to look for this divided by this divide this. So of course, according to this, RA divided by RB is equal to the area ABC, perimeter of BDC, area of BDC, perimeter of ABC. ABC. This is the answer we're looking for, guys. Okay, now, how do you get the areas? Okay, now hear you out. Since this is an angle bisector, this, the great egg in the foot here, this will be equal to, this is equal to this, right? So, let's say these have the same height, well, but the side of these are 3 and 4 respectively. So the ratio of the areas, this to this will be 3 to 3 on 4. So of course this will be 3 on 4. So we simplify this is 3p BDC and 4p ABC. Okay, now for a perimeter part. Let's see here. You know, this is 3, this is 4 black, or the perimeters. Orson, I need to think. Let's see, this BD and AD. These two angles are the same. Okay, now, according to the sine rule, is it called the sine rule? Sorry, I forgot. I don't know what that is called anyway. I never studied math and English, but yeah, let's just say that. This side, which is 4, divided by this, the angle opposite to this side, sine BDC, is equal to BD, this side, I divide by sine BDC, which is, well, 45 degrees, which is the reciprocal of root 2, so I'm going to put root 2 here, BD. Okay, the root 2 BD. Now, similarly, we have 3 divided by sine ADC equals root 2 AD. Now, see here, there are BDC and ADC. They're supplementary angles, right? They add up to 180. They're supplementary angles, which means sine BDC is equal to sine ADC. So, we put sine So we move the sine A, B sine part a bit. We get sine BDC equals sine ADC equals 4 divided by root 2 is 2 root 2, right? 4 divided by root 2, 2 root 2. BD equals 3 divided by root 2 is 2 over 3 root 2. AD. So of course, then what does that mean? Well, that means BD AD by BD is equal to 3 root 2 is 2 times. Yeah, we move this over here. These two split places, basically. Also equals 3b4. These two also. Okay, actually that's pretty obvious. Yes, actually. I basically just did this over explanation, but of course this works for practically any angle bisector. Okay, if there's an angle bisector, then the ratio between this and this is equal to the ratio of this and this. I just proved this one more time. Okay, so this is 3/4. Here are the areas 3/4. Now, we just have to figure out what this now. So we know what BD is, right? BD is 5, but please. So now it's 7, and because 3 plus 4 is 7. 7 is 4 times 5, 20 is 7, 15. If you add these two up, you get 35 over 7, which is, well, 5, so it works. Now we just have to figure out what this is. Fortunately, we could just use the sine rule all over again. Now, according to this is we could plot the BD and AD in, and do get this sine BDC or ADC, or I'm just going to use BDC from here on. Sine BDC is equal to, you plug in the BD, then you get 10, 7 root 2, right? And so this 4 divided by sine BDC thing would also equal this angle, this side, by this angle. This angle was sine this angle. And then we all remember SOHCAHTOA, right? So opposite hypotenuse is 3, hypotenuse is 5, 3, 5. Or we could just write like this. Root 2 BD equals 5 CD to E whatever. BD is 7 to 20. So 7 20 root 2 is equal to 3 5 CD. 3 5 CD. CD will be equal to 3 20 root 2 7 4 3 4 is 12 7 12 root 2 over 7. So of course so we can now get the perimeters here. Calculate the perimeters. The perimeter of this BDC P1 is let me write this here. 4 plus well, the perimeter of this one is 3 plus 7 15 plus again. So our final answer would be what we end up with. And first, we just do some paper calculation here. I'm not even going to write the calculations down. 7 is 21. It's 15 plus 28 plus 20 plus you should get 4 plus root 2, 3 plus root 2. Of course, now, the problem wants us to write the answer that out with no square roots in the denominator. So, of course, we multiply both by, well, 3 minus 2. The root 3 minus root 2, that is. 3 minus root 2. The denominator becomes, well, 3 squared minus 2, 7. The numerator becomes 4, 3, 12. 12 plus 3 minus 2, 10 minus root 2, 2. 10 minus root 2 divided by 7. Of course, okay, I forgot to multiply by this 3e divided by 4 things, so we're going to do that right now. 4 things, so we're left with 28, 10 minus root 2. So, we're going to pick A. Oops. Sorry, I had to. Problem 21. A permutation A1, A2, A3, A4, A5, 1, 2, 3, 4, 5 is heavy-tailed if A1 plus A2 is less than A4 plus A5. Heavy-tailed because, well, the tail is bigger than the head. Actually, I wouldn't call this heavy-tailed. I would call this light-headed. just for a pun, you know. Why heavy-tailed when you could go for light-headed? Now, besides light-headed, we will also have heavy-headed ones, right? Was the number of heavy-tailed permutations. Heavy-tailed is a bad name. Okay, hey, come on, light-headed. Now, if there are light-headed ones, there are also heavy-headed ones, right? Headed one. And the number of heavy-headed permutations is equal to the number of light-headed permutations. Yeah, I'm just going to call all them light-headed permutations for the rest of this problem. They really missed this opportunity here. Now, because of symmetry, their numbers should be equal. For every light-headed permutation, there's also a heavy-headed permutation to go with it. You just reverse it. Reverse the light-headed permutation, you get heavy-headed permutation. Like 1, 2, 3, 4, 5. This is the light-headed permutation, or heavy-tailed, or whatever. You reverse it. 5, 4, 3, 2, 1. There. Now you get heavy-headed permutation. So according to now, of course, there's also the situation where this is symmetrical, where the head and tail are equal weight. Okay, now the total number of permutations is of course 5 factorial. So we know heavy-headed plus light-headed. You know what? I'm just going to call these heavy-headed H plus light-headed plus, well, it's symmetrical. The symmetrical situation with heads equal tails. If heads is equal to tails, well, I'm just going to call that coin-like. Because, well, when you flip a coin, the probability of getting heads is the same as getting tails, so I'll just call coin-like. C, represented by C here. Now, all of these, there are only 3 types of permutations, so if you add them up, it should yield 5 factorial. Now, we already know H is equal to L, right? So we replace them all with L, 2L. We're looking for L, by the way. 2L plus C equals 5 factorial. Well, I'm just going to write X 120, okay? Now, what is C? So basically, effectively turn probability to what is C. We want to know what is C. What is the number of coin-like permutations? So these are 2 head spots. There's a middle spot that we don't care about. And these are 2 tail spots. Now, let's see. What's an example of a coin-like permutation? We could either have 1, 4, and 2. We want the sum of these 2 to be equal to the sum of these 2. So they're so they either add to 5 or they add to 6, because you can't add to 4, because then we will only have 1, 3, and 2, 2. You can't use 2 twice. So it has to be at least 5, which would have 1, 4, and 2, 3. Or we could add to 5, 1, 5, and 2, 4. Now let's do the 5 first. Now there's 1 and 1 plus 4 on one side, and 4 but 2 plus 3 on the other. Now this would also be 4. Now the order of these 2 doesn't matter. It could be 1 plus 4 or 4 plus 1. It could also be 2 plus 3 or 3 plus 2. So of course this would be 2 times 2, right? It would be 2 times 2. But You can also put 1 plus 4 on this side and 2 plus 3 on this side. So that will also be a 2. There are two situations here. So 2 times 2 times 2, 8. Now you can also do 1 plus 5 and 2 plus 4, with a similar logic is also 8. So C equals 16. There are 16 core-like permutations. So 2L plus 60 equals 120. 2L equals 104. L equals 52. Okay. Wait, hold up. There's also the sevens. Okay, I forgot the sevens. Forgot that sevens even exist. Okay, there's also 2 plus 5. And 3 plus 4. Yeah, there's sevens. There's sevens. Always forgot. So there's another 8, which C is not 60. C is 3. 3 times 8 is 24. So you get this. This is not 60. This is 24. So 2L isn't 104. 2L is 96. So L is not 52. L is 48. We picked D. Anyway, next question. Problem 22. A round table has radius 4. Radius 6. 6 rectangular placemats are placed on the table. Each placemat has width 1 and length x as shown. They are positioned so that each mat has 2 corners on the end of the table. These 2 corners be the endpoints of the same side of length x. Furthermore, the mats are positioned so that at the inner corners of each touch an inner corner of the adjacent mat. Wait, what? What does this mean? What's this supposed to mean? Inner corner. Well, I need to think about it. Oh, so these are the inner corners, okay? This is the inner core. These are the inner corners. Inner corners. We're talking about these. Oh, these are the outer corners. Yeah. Anyway, so they want us to find x, right? Now, since this is a regular hexagon, this should be, of course, 120 degrees. So this should be 60 degrees since both of these are 90. So this should be an equilateral triangle with side lengths all being 1. Anyways, this is the center of this circle and the hexagon. Now let's see here. Okay, we construct this inner circle. The circle on the inside. We can actually constructing the outer circle of this hexagon, but whatever. Okay, so this is x. Now this will also, now of course according to meters, this will also be equilateral, right? So this circle has radius x. Now of course if we extend this line, you see that x plus the height plus, let's say, the height of this equilateral triangle is h. X plus h equals the radius of this big circle, 4. Now what is h? H, yeah, equilateral triangle here. This is 1, 1, 1. This is h. H will obviously be, so x equals 4 minus, then there's no such answer. That's not a choice. How? How's that not a choice? Okay. Let's see, each placement has. What did I do wrong anyway? Is the radius of this not x? I mean, this is literally a regular hexagon. How could this, how could this not be x? This has to be x, and this has to be equilateral because 120, because it's 120 degrees, 9 degrees, 9 degrees, 60 degrees. These and this is, and well, both of these are 1, so this has to be 1. This is equilateral with the height of height. I feel like it's the question that's wrong, not my answer of it. Okay, I get it now. Look, look, if we enlarge this part here, yeah, this is the equilateral triangle angle. But we're not supposed to. This is the 2 and the 2 and 3 whatever that we just got. But the circle actually reaches slightly over here, so we can, so it's not 4 yet. If we're doing the center to up to here, it's close to 4, but it's not 4. It's not 4 yet. Okay. 4. So it's not 4 r minus 2 to whatever. But it's definitely close to it. It's definitely close. It's really close to 4. So this is not really close to 4 minus this. Neither is this. Oh yeah, not this. It's actually maybe this. Maybe this. This is slightly. It's gonna be slightly smaller than this, right? And this is slightly smaller than. So yeah, we can keep this. Let's keep this as well. What about this? 2 root 5? 2 root 5, that's 2, we think 2 root 5 is 2.3 or 3, so basically 4.6 minus 1.7, 3.9. 3.9. I think it's slightly bigger than 3. This is, so, no, it's 2.9. 2.9 is approximately. Yeah, we keep all three of those. These two, not these two. Nope. Nope. Anyway, so it's definitely it's gonna be one of these three, right? Okay. Let's see here. Hmm. How do we get? How do we get? This is okay. We know this is x. The radius is x. This is x. Come on. Now, we need to construct this as to construct some convenient triangle where we could just sort out x in an easy way. Hmm. Convenient triangle, yeah, maybe I should just yes, okay, I think I got it. This is x. We put this will be, this is 4, right? This is, no, this is 4, and this is the diagonal of this rectangle over here. The diagonal of a rectangle. You know what that is, right? Okay. And this is 60 degrees. The diagonal of this is going to be x squared plus 1 root by Pythagoras. So according to that cosine law, whatever that's called, anyways, x squared plus 1 is equal to this squared equals this squared plus this squared minus 2 times 4 times x times cosine 60 degrees. Cosine 60 degrees is 1/2. So these two cancel each other out. We have 4x equals 15. Wait, what? Okay, now this is just getting ridiculous. 4x equals 15. What's the heck? That's not an answer either. I need to this more clearly. Clearly. Okay, this is not 60 degrees. That was not 60 degrees. But, oh yeah, this is. I keep making clumsy mistakes like this. It is a problem. Honestly, I actually don't have any idea to solve this problem. Really, I'm probably just gonna go down some long routes for like another 10 minutes or so, because for now I have absolutely no idea. Let me think. Okay. see here, what if we use this triangle instead? Yeah, this is still 4x, and this is 1. This is way more convenient. I think I just held a base area ball. I completely forgot about this triangle. Triangle. This is x for what? This is 150 degrees because, well, this is 90, this is 60, this is 150 degrees. Oh man, I hold the biggest area ball ever. So of course, cosine theory, cosine law again. And these two and this 16 equals x squared plus 1 minus 2 times x times 1 times negative root 32 negative root 32 because there's a cosine of 150. So this turns into x squared, this minus this becomes a plus minus 15 equals 0. Okay, now it's a quadratic. Let's see here. You just plug in the formula. This is root 3 squared minus 15 times 4. Okay, plus 15 times 4. 60. 63. This is root 63, which is just negative divided by, let's 2 divided by, 2. Now, do you have an answer for that? Yes, we do. Oh, in fact, we're using the plus here. The plus for us here. This is the plus. So, yeah, it's C. We pick C. Problem 23. There are so much time you'll use. The solutions of the equation z to the fourth plus 4z to the third I. Okay, so complex numbers. Yeah, complex polynomials. No worries, we can do this. We're gonna try to factor this thing out. Okay, we're gonna try to factor this thing out. And it actually seems pretty easy. Here, look. You know what z plus 1 to the fourth, do you know what that is? That's equal to z to the fourth plus 4z to the third plus 6z to the 2 to the second plus 4z z plus 1. Tell me you see how similar that is. Tell me you see the similarity. Okay, now what if we do z minus 1? Now, z plus 1 is like that. Like the coefficients are basically the same with some signs. Now, what if, let's say, x to the fourth equals, let's replace this with negative I to the fourth root. Yeah, because yes. Negative I to the fourth root. That, I think that might not, that probably not, it won't work. Okay, let's see, what if, now, hmm, yeah, it's probably not a fourth power thing, but it could be some z plus y, but it's going to be equals z plus y times c plus I plus times c plus negative 1. That's the, yeah, that sort of thing. That we could see. In fact, I think, I think it's z plus 1 times z plus I to the third. I think, I don't even think there's any minuses here because, well, if there's minus, it will break the 464 thing. 4. Let's try it out, okay? Z plus I to the third, that's z to the third plus z to the second I minus z minus I. This is z plus 1. This is the z third, z, no, z fourth, plus z third I minus z I. And then we plus this thing. We actually, no. Let's see, okay, see. I feel like this thing is hard to factorize. Wait, actually, I forgot. Okay, I forgot the coefficients here. This is 3z, 3z. I think I'm in this math, in this problem solving thing today right now. But yeah, this is z4 plus z3. Well, it still doesn't explain stuff. Explain though. Oh, wait, hold on. Okay, yeah, maybe let's try stop trying to factorize this and try I find a similar factorial. Now, of course, we already have that. We know the ODEC. Yeah. It's pretty similar to z plus I to the fourth power. Okay, yeah. Okay, I think it's similar to z plus 1 to the 4I to the fourth power, right? Because z plus as the fourth power is z fourth plus 4z through e3I minus 6z 4zi plus 1. It's similar to this, but this plus 1 is replaced with negative I. So we take away 1, and now it becomes this part without the 1. and then we minus I, and then it just becomes this. See? So in fact, we just turn this whole thing into, we transform this into z plus I to the fourth power equals 1 plus I. Alright, okay. So so this is a huge step now. Pretty much, this problem is pretty much half solved. Z, now you just need to figure out all the solutions for Z. Z plus I. Z plus I equals I to the fourth equals 1 plus I. Now, it's similar to Z to the fourth equals 1 plus I, but it's actually similar to Z to the fourth equals 1 plus I, but everything is moved everything is moved one down. So anyways, let's draw this. We should look for the Z to the fourth equals 1 plus I first. Then the roots then you just take one from them, you take one from each of their roots and you get the 4 roots to this. So we need to solve this first. 1, 2, 3, 4, 5, I, 2I. Why am I using X and Y for this? With this? Oh no, it's just coordinates. I like using X and Y. I'm used to using X and Y. 4I. 5I. -1. -1. And stop. Okay, -I. This is now. Z for this 1 equals 1 plus I. Let's say 1 is where is 1 plus I? It's here, right? This is the point. This will be 45 degrees. With 45 degrees. Now this is this is root 2. The magnitude is root 2, so we then put that in the root 4. Root 4. Then we root that by 4. It's 2 to root 2 to root 2 root 8. It's gonna be extremely close to 1, but it's not gonna be 1. Anyways, this we have to quarter this angle. So quarter this angle is about here. This point is going to be about here. Where's their other 3 roots? Well, because symmetry, the other 3 roots will be here, 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 and here. That's literally how complex number works. Because at this point, if you spin it, you go here, then spin again, you end up here. Then spin again, you end up here, right? This is the same thing. It's equal to this plus this. This, if you spin this thing 4 times, it ends up here. But if you spin this times, it ends up here, and you add up, still here. Yeah, you got So this is that quadrilateral. These are the four roots to the to this z form equals 1 plus I polynomial. Now, now if you want the roots to this, we just move everything down. The four roots to this will be this is just demonstration. We don't really need to do that. And since of course the area is going to be the same with both of these, it is the yeah. Okay, now we know the magnitude. We know this diagonal here is equal to this thing, or just 2 to the 1/8. Now, tell me what's the area of this triangle? The area of this triangle will of course be to this times this 2 so 2 to the 4, or it's the fourth root of 2. It will divide by 2, so it's minus 1, 2 to the negative 2 to the negative 4, 3. And then you times that by 2 to the, actually raise that this, times 2. And then you want 4 of these triangles, so you multiply by 4 again. This is 4, so this is 2, 4, 2, 1/4 plus 1. What do you pick? D. Triangle ABC has angle C equals 60 degrees and BC equals 4. Point D is the midpoint of BC. What's the largest possible value of tangent to GAD? Okay, let's draw this diagram. BC. BC equals 4 is 60 degrees. And 4, so D is the midpoint of BC, so this is the it splits it in half, so this is the midpoint, it splits it in half, 2, 2. What's the largest possible value of tan BAD? Okay, so we know that A is going to be on this line, this ray. It's going to be on this line. It's somewhere on this line where it can move. It can move on this line. Tangent BAD. Now, if we want the large value of tangent BAD, do we want a small BAD or a large BAD? Do you remember BAD? BAD has to be accurate. It literally has to be accurate. It literally can't be obtuse. So it's an accurate angle. For an accurate angle, if we want the tangent to be big, should the angle be bigger as possible? Yes, we want the biggest angle BAD possible. So we want the biggest angle. So this is not the biggest. BAD. These could all be E potential A's. Now, when do we get the biggest angle? Let's think. Okay, I think it's time we put coordinates into the play. Yep, coordinates. You say C is the origin, okay? But C is the best letter, so it's fitting. C is the origin. This is the X, this is the Y. Alright, now of course, let's this become B. C is, of course, 0, 0. B is, this is 4, 4, 0. And D is 2, 0. Now this line AC, the line A is on, A is going to be on line. A is going to be on this line here. So the coordinates of A will be, well, let's just say X root 3X. X root 3X, because while it's equilateral triangles, 60-degree angles, it's like a property of 60-degree angles. So if this is X, this angles. If this is X, this has to be root 3X. BAD. This is BAG. This is the angles here. So tan BAD, we know BAD is equal to 180 degrees minus ABD, ED minus ABB. We also know that tangent in 180 degrees minus something minus alpha is equal to Well, negative. Negative tangent alpha. So this is going to be tangent ABD plus ABB. Now these two is easy to make out. These two angles will be easy to make out because you have is equal to cosine sine cosine sine cosine sine equals to 1 minus tangent ABD tangent ABB. On the top, we're going to have tangent ABB plus tangent ABB. Now we're going to try to find these tangents, okay? Tangent ABD, that's just, tangent ABD, that's just we made this down here. This is foot. This is right angle. So we know SOHCAHTOA opposite is SOHCAHTOA. This will be 8 coordinates because there's 3x. This is an x. Having x point this way is pretty confusing. But I'm going to draw this. I'm going to draw another diagram. But with x pointing the other way. B, this is D, C, and A is on this line. A is somewhere on this line. 2, 4, 0. Now, based on SOHCAHTOA, we want this ABD, ABD. ABD. We move this down. This is ABD. This divided by this. This is root 3x. This is, point this x minus it's one. No. Oops. Yeah, this is D and this is B. I make so many careless mistakes. So here it's okay. So ABD is this one. This is ABD. So opposite is, so this is just still gonna be just 4 minus something. 4 minus x. Now what is tangent ADB? Tangent ADB is going to be root 3x. 4 minus x this time is this thing. It's going to be x minus 2. Root 3x is always going to be still root 3x. Okay, now we plug these into this equation. We got something full of x's. So let's do the plugging, shall we? Hope you got your paper ready, because it's gonna get I'm literally running out of paper. I'm running out of space. Anyways, hold on, let me do this in another document. We multiply both on the numerator and the denominator by this thing. And so the numerator becomes, well, these two cancel out. And then the 4x minus 8 minus x squared plus 2x, right? Minus 3x squared. So it's still going to be, the bottom will turn to negative x squared, negative 4x squared. Plus 6x minus 8. We'll simplify this down to root 3x. Negative root 3x. X. 2x squared plus 3x. Minus 3x plus 4. Go back. Okay, now we have this. So now we want the negative of that. And if you forgot, we want the negative of this. So we remove the negative sign here. Here now. We can remove the negative sign here now. So now we get this thing. This is the value of tan BAD. Now we want the largest possible value. Now we get the largest possible value. How do we get the largest possible value of this thing? Like, do we have to calculus this? I don't want to do calculus here, okay? Not all of you who know calculus will do this. This does not. I thought it said this does not require calculus. How do we do this then? Let's see. We separate this thing somehow. Want the largest possible value. The largest value. Largest value. It needs to be big. To be biggest. So we want this to be the smallest. Okay, I think I get. I think it's supposed to be it's supposed to use AMGM inequality here. So we turn this into the reciprocal. This is 3x root 3x 2x squared minus 3x plus. I'm just gonna. I think I should do it on the other page. Yeah, other page. Yeah, doing that on the other page. Erase it. Erase all of this. Okay, okay. No more negative sign. X. This is equal to 1. 1. Equal. 1. This equals X plus 3x minus root 3. Minus root 3. Okay. Okay, now if we apply that rest of the AMGM inequality here, yeah, this is going to be less than or equal to well, we know it's all positive, so it has to be less than or equal to, right? Like, if this is greater than or equal to, then this whole thing is going to be less than or equal to. That's the logic here, because here it's divided by the reciprocals. So now we have 2 and square root x times root 3 x 4. And then this. The x's will cancel out. And out we have 2, 4, 8. 3, 8 minus root 3. Four root 2. This instead of 3 we multiply. We turn it into 9. This is 24. Still 1. 3. 2. We can factor out. What can you factor out? We can factor out 4. This becomes a 2. 2 2 is 4. 6. Okay. So that's it. Yep, and we have to turn it into something else. We multiply both. We multiply it all by, say, root 3, I guess. Okay, this is root 3. Or root 2 minus 3. You have the answer? Yes! It's D. Okay, I've been doing all of this for like 1.5 hours now. I'm running out of time. But I guess we should do an individual video for problem 25. I'm just gonna end the video here, okay? Bye.